Hello, this is um, lesson 7.2, and we're going to be talking about linear programming with the graphical method. So first, we're going to define goal of optimization. So we are trying to find the largest maximum or smallest minimum value of functions, such as profit functions, cost functions, or revenue functions. So a little bit about terminology. We have a object objective function. So the function which can be a cost, profit, or so on, for which a maximum or minimum value must be found. We want to optimize this function. And usually it is written as z equals something. Now, there's going to be constraints. So functions that represent various limitations. For example, transportation costs, environmental protection laws, availability of parts, interest rates, etc. Now, consider the objective function below. We have z equals 2x plus 5y. So suppose z represents cost, which you want to minimize or maximize it over a feasible region. Well, if it's the cost that it represents, we want to minimize it, of course, because we want to minimize all costs. Now, suppose z represents profit, which you want to minimize or maximize it over a feasible region. Well, of course, if it's profit, we want to maximize it. So that's what this means, that it can be or we're trying to look at our objective function and then either minimize it or maximizing it. Okay, so um, we're going to start kind of looking at the feasible regions one thing at a time, and then we'll put all that together on our last example. So first, we're going to start looking at corner points. So we have the reasonable feature, sorry, feasible region defined by the given constraints graphed below here. What we've got are, or first we have our equations here, or inequalities, I'm sorry, inequalities here. So if we look at, they've already graphed it. So we have, for example, our first inequality 3x plus 2y is less than or equal to 6. The boundary line is right here. Our second negative 2x plus 4y is less than or equal to 8 is right here. And then we've got our third one, which is x plus y is greater than or equal to 1. That one is right here. And then we've got our two other ones. So we have x is greater than or equal to 0, which means that that one is right here. And we have our y is greater than or equal to 0. Sorry, I wrote it the wrong way. Of course, x is greater than 0 is this one right here. And y is greater than 0 is this part right here. So this is that's number 5, and this is number 4. There we go. Okay, so now they have defined the objective function for us. So that is z equals 2x plus 5y. Now, if a max or a minimum value exists, it will always occur at a corner point. So what we need to do is we need to look at the corner points. And before we actually do, notice that this is a bounded region. So that means that it's enclosed on all sides. There's not a open side here. Okay, so let's look at those corner points. Um, we have this one right here, which is 0, 1. We have this one, which is 0, 2. Then we've got this point right here, which we don't actually have an exact value. It's going to be a decimal. This one here is 1, 0, and this one is 2, 0. So we have 1, 2, 1, 2, 3, 4, and 5 corner points. So how would you find the values of the corner points? How do we do that? They're the points of intersection. So that means that it's the solution to system of equations, right? That's where, for example, this 2, 0, that's where the x is greater than 0 and our 3x plus 2y equals 6 intersects each other. So that's how we find the corner points. Okay, so let's look at what's called corner point theorem. So if the feasible region is bounded, then the objective function has both a maximum and a minimum value, and each occurs at one or more corner points. If the feasible region is unbounded, the objective function may not have a maximum or a minimum, but if a maximum or a minimum value exists, it will occur at one or more corner points. Okay, so next we're going to look at optimizing the objective function. So we are using the feasible regions shown to find maximum and minimum values of each given objective function. So what we're going to do here is we're going to start with this corner point right here, 5, 10. And we're going to plug it in to the objective function. So in corner point 1, z is going to be, oops, well, it doesn't keep it, 6 times our x is 5 and our y is 10, so plus 10. So our answer is 30. Next point, we'll take this as our second one. So z equals 6 times 6 plus 3. So 36 plus 3 is 39. Then we'll take this point right here, 1, 1. Z is 6 times 1 plus 1, which is 7. And point number 4, 2, 7. Z is 6 times 2 plus 7 equals 19. Okay, so now we're going to look at the z's that we got. We can see that our maximum is 40. So our maximum value is 40. It is at 0.510. Our minimum is going to be 7, and that is at 0.11. Okay, let's do the same thing over here on the right side. So we have z equals 0.35x plus 1.25y. Let's start with the 0.618. Again, we're plugging it in. So 0.35 times 6 plus 1.25 times 18, we get 24.6. Let's take this as 0.2. So 10.9 z equals 0.35 times 10 plus 1.25 times 9. Plug it in the calculator, and we get 14.75. 3 is 12, or we're going to take the 0.120. So 0.35 times 12 plus 1.25 times 0 equals 4.2. 4 is going to be the origin, 0, 0. So 0.35 times 0 plus 1.25 times 0, which is going to be a 0. And then 5 is right here, which is z is 0.35 times 0 plus 1.25 is 15. And that equals 18.75. Okay, our maximum value is 24.6, and it is at the 0.618. Our minimum value is going to be 0, and that value is at 0, 0. Okay, so that's how we find the minimum value, maximum, and where they are located. Next, we're going to look at finding the corner points. Um, Again, we're identifying the system that needs to be solved to find each corner point. Now, looking at this feasible region, we can see from the graph that this is bounded. Okay, we're first going to start with corner point A. A is right here. That is the intersection of x equals 3 and y minus 2x equals 2. Then we're going to look at corner point B, which is the intersection of x equals 3 and this line 3y minus 2x equals 0. Because those two lines, so if this line and our x equals 3, that is where those two intersect at point B. Okay, where's our C? Right here. So we've got this one right here, which is y plus 8x equals 52. And then we have the, 3y minus 2x equals 0. For D, we have this line right here, which is the y plus 8x equals 52. And then we have our y minus 2x equals 2. So what we did here is we identified the system that needs to be solved to find each corner point. That's all we were asked to do. Again, we're doing it step by step. We'll put all this together with the last example. Okay, so moving forward, determine the feasible region and then identify the corner points and minimize the objective function. So since we are asked to minimize our objective function here, we could think that this is probably a cost function, right? Because that's something that we want minimized. Okay, so if we look at this feasible region here, that's been graphed, it is bounded. Now, although before we actually do that, we want to make sure that it actually is bounded. We want to make sure that we're it is the correct, or it is in between. If we look at x plus y is less than or equal to 10, what we need to do is we need to take a test point. And again, if we can, we're going to use 0, 0 as our test point. So we're going to plug in test point 0, 0 to x plus y is less than or equal to 10. 0 plus 0, well, that is less than or equal to 10. So we know that this is true. So from this one right here, we would be shading this way towards or the area where 0, 0 is. Okay, let's take our next one, which is 3x plus 2y is greater than 6. We're going to use the exact same test point for that one because, again, it's not on that line. 3x plus 2y is greater than or equal to 6. So 3 times 0 plus 2 times 0 is greater than or equal to 6. Well, this is false. So the point 0, 0 is not in the shaded. So we would be shading away from that point, this direction. Okay, we've got two more. So we have our x is greater than 0. That would be shading this way right here. And then we have y is greater than 0, and that would be shading this way also. So now we know that our feasible region is inside all of these, which means that it is bounded. Okay, next we're going to calculate the or minimize the objective function. Sorry. So before we can do that, we need the points. So let's look at what points we've got here. We have 2, 0 is one of our points. This here is another one, 10, 0. Then when we go up, we've got 0, 3, and we have 0, 10. So we have 4 corner points here. And let's do A, B, C, and D. Okay, so now we're going to use our objective function. We're going to plug in A first. Z equals 0 plus 2 times 10, which is 20. Our point B is right here at 10, 0. So 10 plus 2 times 0, which is 10. C is going to be 2 plus 2 times 0, which is 2. And D is going to be 0 plus 2 times 3, which is 6. So we can see that this is our minimum right here. So our minimum is going to be at 2, 0. That would be our answer. It says identify the corner points and minimize the objective function. Okay, so now you might take a look at the graph and go like, okay, well, that's pretty obvious. Now, make sure you still do the calculations and show the work that you are. Sometimes there might be a surprise what the actual minimum or maximum value is depending on the graph and the feasible region. All right, now we're going to put all this together. So solving a linear programming problem graphically. First, we're going to write the objective function and all necessary constraints. Second, graph the feasible region. 3, determine the coordinates of each corner point. 4, find the value of the objective function at each corner point. And then 5, if the feasible region is bounded, the solution is given by the corner point producing the optimum value of the objective. Now, these constraints are the inequalities. That's what it is. And again, a reminder, the objective function is the z equals something. Okay, so let's go ahead and look at this example right here. We have our objective function right here. Again, it is given to us. Now, if we look at it, it is, again, we are minimizing it, so it probably is a cost function. Oops. Here we are given the constraints. And now, before we start graphing these, notice that every single one of them has the equal sign with the inequality. So they are all solid lines. So when we graph them, we can graph them as solid lines. Now, one more thing. When we start graphing, so we have a coordinate plane here. When we start graphing these, they are always in the first quadrant. So we don't go into any other quadrants. We're going to graph it in the first quadrant. All right, so let's start with this first one here. So we have 2x plus y is less than or equal to, actually, I'm going to write it as an equation now, and that should be a 10. 2x plus y equals 10. So we're actually graphing the boundary line. I'm going to move the 2x to the other side. So I get it in slope-intercept form, which helps graphing. So y equals negative 2x plus 10. We're going to have to do something about this graph, though, before we do anything. So we have our x-axis, and we have our y-axis up here. I'm going to do these 2, 4, 6, 8, 10, 12. You know what? Let me do it a little bit differently. Let's see if we can fit 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Up here, 1, 2, 3, 4, 5, 6, 7, ouch, 8, 9. We're going to need that 10 up here. Because if we look at our line right here, the y-intercept is right here. So it's 0, 10. Our slope is negative 2, so it's going to go down. So down 2 and to the right 1. That's not correct. Over all the way here. Again, down 2 and right 1. Down 2 and right 1. Down 2 and right 1. Here we go. Okay, let's see. Graphing up. Almost straight line. A little bit of a shaky hand. Okay, so this here is our 2x plus y equals 10. Now, the point 0, 0 is not on the line, so what we can do is we can test that. So we're going to use test point 0, 0 so that we know which way we are shading. So 2 times 0 plus 0 is less than or equal to 10. 0 is less than or equal to 10. This is true. So 0, 0 is included in the shading, so we would be shading this way. Okay, let's look at number 2. Number 2 here is going to be 5x plus 2y equals 20. This one, I'm just going to go ahead and find the x and y intercepts. I feel like that might be easier. So 5 times 0 plus 2y equals 20. So y equals 10. So our point is 0, 10. And then we're going to do y equals 0. So 5x plus 2 times 0 equals 20. So x equals 4. So 4 and 0. So 0 and 10 still over here, and 4 and 0 is over here. Okay, this is going to be interesting to try to, yeah, exactly. There we go. Okay, so that line is 5x plus 2y equals 20. We need our test point, so we know which way we are shading. So test point 0, 0. 5 times 0 plus 2 times 0 is greater than or equal to 20. Well, 0 is not greater than 20, so that is false. So we are shading away from point 0, 0 this way. Okay, next one is over here. So our third is negative x plus 2y equals 0. I'm going to do the x and y intercepts for this one as well. So negative 0 plus 2y equals 0. Well, that gives us y equals 0. So we know that one of them is 0, 0. So that doesn't help us because it starts at 0, 0. And that's both the y and the x intercept. So we're going to have to either calculate another point, which actually we could do. We could, for example, plug in 4, x equals 4. So we get negative 4 plus 2y equals 0. 2y equals 4. When we move the 4, y equals 2. So one of our points is 4, 2. So I just chose a random point. That's what I did. 4 and 2 would be right here. And we would graph the line this way. So this line is negative x plus 2y equals 0. Now, we need another test point. We cannot use 0, 0 because that's included on the line. What I'm going to do is I'm going to use the next easy one. So I'll just plug in 1, 1. What do we have? It's negative 1 plus 2 times 1 is greater than or equal to 0. So 1 is greater than or equal to 0. This is true. So we would be shading this way over here. Now, we still have the constraints of x is greater than 0 and y is greater than 0 over here. We don't necessarily need those because if we look at this, we already have a shaded region which would be inside this triangle right here. All the way. This is not the best because the lines are not straight, but this is where it would be. Okay, so what we need to do now is we need to figure out these points. We know that this point is 0, 10. That's on there. We do not know what this point is or what this point is. So we're going to have to do some calculations here. Solve systems with the two equations. So with B, the point B here, we are using, or it's an intersection between the 2x plus y equals 10 and the negative x plus 2y equals 0. Okay, so we have a couple of options here on how to solve these. What we're going to do is let's multiply this by 2. Yes, so we get 2, not 2x, not this one by 2. I'm sorry. Multiply this by negative 2 is what I was going to say. So we get negative 4x minus 2y equals negative 20. And the other one is negative x plus 2y equals 0. Now we can go ahead and add. Our y's cancel out. We get negative 5x equals negative 20. So our x is going to be 4. Now what we're going to do is we're going to go ahead and plug this in to one of the original ones. I'm going to go ahead and plug it in to this one right here. So negative 4 plus 2y equals 0. 2y equals 4. So our y equals 2. So our point is going to be 4, 2. That's what this corner point right here. And if we look at it, that is where it looks to be. Okay, we need another corner point, which is this corner point C here. That one is the intersection of negative x plus 2y equals 0 and our other one, which is the 5x, hold on, 5x plus 2y equals 20. Yes, I was like, plus 2y equals 20. Okay, so the same thing, we have a system of equations, which we need to solve here. I'm going to multiply the top one by negative 1, so x minus 2y equals 0. The bottom one did not change, but when we multiplied the top one, these cancel each other out, and that's our goal. 6x equals 20. So we divide by 6, we get x equals 20 over 6, which simplifies to 10 over 3. Okay, fractions. So our x is 10 over or 10 thirds. I'm going to go ahead and plug it into this top one. Negative 10 thirds plus 2y equals 0. So 2y equals negative 10 thirds. We need to divide both by 2, and we end up with negative 5 thirds. Hold on a second. It shouldn't be a negative. Where did I go wrong? Oh, this should be a positive, of course, because I'm moving it. So our point C is 10 thirds and 5 thirds. So it's this point right here. 10 thirds and, come on. So point C is 10 thirds and 5 thirds. Yeah, they both have to be positive because it is in the first quadrant where both x and y are positive. Okay, so we are supposed to minimize. So what we're going to do is we're going to take all of these 3 points here. So 4, 2, 10 thirds, and 5 thirds. And then we had our 0, 10, and see which one is the one that gives us the minimum value. Okay, so we are minimizing z equals x plus 3y. That was given to us right here. Let's start with this point A, which is 0, 10. So z is 0 plus 3 times 10, which is 30. Our point B here is 4, 2. Plug that in. 4 plus 3 times 2, and that is 10. And then our C is the one with the fractions, not a plus. There we go. Z equals 10 thirds plus 3 times 5 thirds. Well, look at that. The 3's cancel each other out. And we get, you can plug this in the calculator. It will give you 25.3, which is 8.3 repeating. So our minimum value is going to be this one. So our minimum is at 10 thirds, 5 thirds, that point. That would be our answer. Okay, that's it for 7.2. Let me know if you have any questions. Bye.